to work out some problems. But before that, I want to talk about this conditional probability. You must have studied that in your 12th standard. Nevertheless, just a brief introduction. So, suppose that B is an event. So let me write. Suppose that omega of B P is a probability space. And B is an event such that probability of B is positive. So let A be also an event. Okay. We say that we define probability of A given B to be. So probability of A given B, A conditional on B, whichever way. So this is probability of A intersection B divided by probability of B. Okay. So in other words, so this is what it is computing is that so this phrase. So let me write that, because probability of A given B. This is how it is pronounced, or probability of A conditional on B. Okay, so one of the two. And what it means is that you already know that event B has occurred, then you want to know what is the probability that A has occurred. So in other words, it's like you have the sample space. Let me draw a diagram. This is your omega, and A is here, and B is here, maybe partly overlapping. It may not overlap also. So this is A intersection B. So once you know that B has occurred, you are already in a smaller region B, and you want to know what is the probability that A has occurred. The only way this A could have occurred is if your favorable region is now shrunk to A intersection B. Okay, so that is why you have this probability of A intersection B, and this one is normalizing factor. Mind you, your new omega has, you can think that your new omega is now your region B. Okay, and therefore you can think of your favorable sets, all possible events when omega has become B is the collection of all, is the collection F intersection B, by which we mean all A intersection B, A in F. Okay, and of course, again, you can think of this function P. So now your new, we regard B and then F intersection A and P of dash given B as our, we regard this as a probability space, new probability space. Okay, this is a more rigorous way of saying what it is. And the interpretation, already we understand what it means. Okay. And yeah, so some observation lemma. Suppose that probability of A is also not equal to 0. Probability of B is also not equal to 0. Then over the two related, probability of A given B is equal to probability of A intersection B divided by B. This is definition. This is same thing as probability of B given A times probability of so this one, probability of A. Actually, I can just compress this in just one. Let's not write like this. I want to say it slightly differently. Probability of A intersection B is equal to probability of A given B times probability of B. Okay, means the same. More generally, if probability of A1, yeah, let me write the condition first. More generally, probability of A1 intersection A2 intersection blah 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 intersection AN, this is equal to, yeah, so probability of A1. So I want to assume something. This is going to be, so you can just say, I'm just going to iterate this process. A1, which way I want to have. Let's write like this: A1 intersection A1 given maybe AN 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 minus 1 times probability of A1 intersection AN minus 1. And you can now repeat this. So ultimately you will get probability of A1 given A2 times probability of A2. I think you will have A2. A1 intersection A2. I'm just trying to run the proof in the reverse before writing it correctly. So let's just write one more step. I think even otherwise I may make fairly simple thing, but I can't remember. No need to remember, just understand that will do. N minus 1 probability of A1 intersection A2 given, sorry.
So the first one is A instead of A1.
Hmm?
It's A1. It's AN instead of A1.
Yeah, yes, that's right. AN. AN. So let me just look at this. I can't remember. I don't know where it is. I should have written it down before coming here. It's a fairly simple thing to prove. It's just simple induction. I think that's it. Mm. Mm. Okay, so here is the answer. So let me just directly write that and then we will know. Okay, so let me write it now that I have noticed what is given. So the next step. Sorry, something happened. Like it's not working.
So I think it will be easier for you to write if you define, let's say, A1 intersection A2 intersection dot 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 till AI as CI, for example. That will be
Yeah,
easier
and
to
sorry,
write it down.
I just it's a very trivial thing to write out, but I just let me write like this: A2 probability of A3 given A1 intersection A2 probability of so on. So A4 given A1 intersection A2 intersection A3 and so on. And finally, you have this probability of A1 AN given A1 intersection AN minus 1. Okay. So provided, so this holds provided probability of AN minus 1 not equal to 0. So that automatically means that the remaining things that appear here, they are all not equal to 0 and therefore you can apply it. So this is, I'm sorry, I just got a little confused while writing this, but it's a very simple thing. So in fact, the proof is obvious. Proof is actually given here. You just write this in this particular way and now substitute for this. Okay, from where? From the same statement, except you use this way, up to probability of an divided by whatever, I mean an minus 1 given a, so that intersection you can just substitute and then you will have proof is by induction, that's it. So only thing to prove is, so proof proof true for, so you prove this, the first statement which we made, A intersection B is equal to probability of, this is obvious, A given B times probability of B. So now use induction. Use induction.
Sir, I think there's a mistake in your statement, sir, in
Yeah,
the previous
there is a
page.
mistake.
Sir, instead of P of A1 given A2, I think it's P of A1 intersection A2.
This statement is wrong. Pn.
No, sir, the next line, the next line.
Next line, A1 given A2, and then A3 given A1 intersection A2, A4 given A1 intersection A2.
Yes, sir, the first thing, P of
First one, you
A1
think it's not
given
correct?
A2. I think that's,
I
yes, sir.
probably miscopied it. Just yeah, okay, you are right. It's actually probability of A1 times. Sorry about that. A1 times A2 given A1. I'm sorry, I just miscopied it. But the proof will show the moment I write. So this is A2 and A1, and here probability of A1. Yeah, that's true. Otherwise, we will get into difficulty with the proof. In fact, very first line itself, we get into the difficulty. Yeah, so here probability of A1, probability of A2 given A1, and then probability of, I suppose now this is okay. Let us prove it because I made a mess. So normally I would not have proved this, but since I made a mess, I wasted 5 minutes of your time. Let me waste another 3 more minutes and finish the proof.
Yes, I think now it's correct, sir.
Now it is okay. I just missed that probability of A1 and then A2 intersect. Yeah. So, okay, proof is by induction, use induction. So suppose that for n equals 2, the way I have written it, B is equal to A1 and A is A2. Okay. So now, so suppose that probability of A1 intersection an minus 1 is equal to probability of A1 times probability of A2 given A1, probability of A3 given A1 intersection A2, and so on. And finally, you write this probability of A n minus 1 given A1 intersection, blah, 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 A n minus 2. Okay. Suppose this, then, okay, so of course, I should put n equals 3 so that I will have A1 intersection A2, that is probability of A1 times probability of A2 given A1, that is correct. Because n minus 2 becomes equals 1, and therefore it's already, it's checked for, so here I may as well suppose n bigger than or equal to 3. Okay, now probability of whatever I wrote earlier in the first step, A1 intersection AN, this is equal to probability of, what did I write? AN intersection AN given A1 up to AN minus 1 times probability of A1 intersection AN minus 1. Substitute for that. So when you substitute it, write it in the reverse order. The commutating probability of A1, probability of A2 given A1, probability of whatever, A3 given A1 intersection A2, and so on, and up to where, yeah, up to here, probability of an minus 1 given a1 intersection an minus 2 times probability of an given a1 intersection blah 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 intersection an minus 1. Okay, finally we got it right. Yeah. So it's a interesting formula and it's very useful actually. Okay. And another useful lemma is the following. This is often called Bayes theorem. So probability of assume probability of A not equal to 0 and also probability of B. And probability of A given B is equal to, you can write of course, probability of A intersection B. Yeah, so divided by probability of, I'll explain, this is equal to probability of, so this occurs B in given A times probability of A divided by, here this you rewrite as probability of B intersection A plus probability of B intersection A complement, and each one of these intersections you can rewrite it in terms of probability of B given A times probability of A. So I'm writing the proof itself as a lemma, but that's the way I can remember. So B given A times probability of A plus probability of B given A complement, probability of A complement. What's the point of this exercise? Sorry, this complement doesn't look nice. The whole thing is, so as you know, it may be, this is useful. So this is useful. This is useful when probability of B given A and probability of B given A complement are easier to compute, or much easier to compute, much easier to compute. And again, so it may be that there's a natural way in which you can generalize it. Instead of just one event, A and A complement, you can have a partition and then express everything in terms of that. So I write also that as a corollary. Just let me get one more page. So, so suppose that, so corollary, suppose this I will not prove, I'll just write it. There is nothing to prove here. Suppose that omega is equal to E1 union En. So where Ei intersection Ej, that is, these are mutually exclusive events, is equal to empty if I is not equal to j, then, and yeah, suppose also probability that of B is not equal to 0 and probability of none of these is 0, not equal to 0. They're all positive Okay. Then probability of, yeah, so E, okay, uh, E given B, this is equal to, so let me write here EI given B, probability of B given EI times probability of EI and divided by summation probability of uh, B given EJ times probability of EJ. And J goes from 1 to N. Okay. So this also is called Bayes' theorem. This is the second simple corollary of that, just repeatedly using, decomposing this. Okay. This comes from where? This comes from probability of, so need only note. What has happened is that probability of B is equal to sum over probability of B intersection EJ, J equals, this is all that is involved in the proof, nothing more. Summation, this is, you rewrite it as B given EJ times probability of EJ. Okay, that's it. That's all that is needed to be noted for the proof, nothing more. And now let us do some problems, exercises. Some of these problems maybe are familiar to you, and nevertheless, for the sake of uh, completeness, I must do these at least a few elementary problems. So two cards are drawn in succession without replacement from a pack of playing cards. As you know, playing cards contain 52 cards. There are 4 suits, and in each suit there are 13 cards or ranks, as they called. So find the probability that the second card drawn is an ace. That's one problem. Find the probability that the second card drawn is an ace, given that the first is an ace. So let us do the first problem. So you have a pack of 52 cards. So question 1, A. So let A be the event. That the second card drawn is an ace. Okay. Of course, the probability that the second card drawn, in order to compute that may depend on the card that was drawn the first time. Okay. And we don't know that, so we just say let B be the event. Event that the first card drawn is an ace. Okay. So we can compute this probability of, so probability of A, second card drawn is same thing as probability of A intersection B plus probability of A intersection B complement. B complement is what? Is even that this first card drawn is not an ace. Okay. But this one, you can compute, express this in terms of conditional probability. Probability of A intersection B is, so A given B times probability of B plus probability of, A given B complement, probability of B complement. Okay. And now you do this. So what is the probability that the first card drawn is an ace? Okay, there are 4 aces, so 4 by 52 is the probability that first card drawn is an ace. Given that the first card drawn is an ace, there are only 3 aces and A, so the favorable events will consist of 3 elementary events, and there are only 51 cards now because one card had been drawn already, so 3 by 51 plus, now given that the first card is not an ace, so there are 4 aces possible out of 51 cards. So 4 by 51 is the probability. Probability that this is not ace, there will be how many? So out of 52 cards, 4 are gone. Remaining is 48. 48 by 52. So you simplify this and you get the answer. Okay. So 51 times 52, 12 plus 200 minus 8, 192, I suppose. Whatever it is. Yeah.
1 by 13, I think.
Did I make a mistake?
Sir, it simplifies to 1 by 13.
1 by?
1 3. 1 by 1 3.
Oh, I see. Okay, you can simplify it, I suppose. Yeah, okay, sure. All right, so you can simplify this. Yeah, this 51 and 52, this 100 and 204. I was not simplifying. Okay, you people can do this better. All right. So what's the other problem? Let me look at that. Find the probability that second card drawn is an ace given that the first is an ace. That's easy. We already did a part of it. So part B, second card drawn is an ace given that the first one is an ace. So this is easy to compute. We did that. So first card drawn. So there'll be first card drawn is an ace. So there are 3 aces remaining, 3 by 51. Okay. I suppose this is 1 by 17.
Hello, sir.
Yes.
Yes, sir, could you show the part B question once again?
Yeah, second card drawn is an ace given that the first card is an ace.
Oh, okay, sir.
It's a fairly simple question. I could have made it complicated. I could have, so you can do that also. Not at all a problem. Well, let's do that. So it's not there. I didn't write it down, but you know how to do it, right? So what is the probability that the first card drawn is an ace, given that the second one is an ace, second card drawn is an ace. Okay, let's do this. Okay, probability of, so this time you want to know B given A, suppose. Yeah. The second card drawn being an ace is the event A. Okay. Well, we know how to do this. This is just by definition, this is probability of B intersection A divided by probability of A, but this is same thing as probability of A given B times probability of B divided by probability of A. You already computed probability of A. I believe your answer because I see that there is some cancellation taking place. 4 in 200. Okay. So substitute that for the denominator. In the denominator, you have 1 by 13. Yeah. So in the numerator, this is probability of B, we know is 4 by 52. And probability of A given B, just now we calculated it. And that is 1 by 17, no? Yeah. So you can simplify this a little. So this is, okay, let's leave it at that and proceed. Probability of B, this I think we have done it right. Okay. Fine. Let's take up another problem. Sorry, I have to go up and down like this because I there are two urns. Yeah, I wanted to do some other problem before discussing this, but anyway, let us do this problem. There are two urns. So urn 1 and urn 2, they contain red balls and black balls. In this composition, 3, 2, and then for urn 2, it is 5 and 4 and 5. Okay. And what is the probability that the ball drawn from urn 2 is black? So that's the question. So what you are doing is you are drawing a ball from urn 1 and then transferring it to urn 2, and then you are computing the probability that the ball drawn from urn 2 after this transfer turns out to be black. Okay, so that's a question. Let us do that. Okay. I wanted to discuss some other problems also, but let's just do this. So question 2, urn 1 and 2. Here red balls and black balls. Okay. And 1, what are the composition? I wrote something, can't remember what I wrote. Maybe pick some random. Number 3, 2, and then 4, 5. Okay. Yeah. So this contains 3 and 2, 4 and 5. Okay. Now a ball is transferred from, this is after transfer, what is the thing? Okay. So I don't want to repeat the problem. It's already written there. Let B2 be the event that the ball drawn, I could have just called it B, a ball drawn from from earn 2 is black. After transfer. Okay. So we need to compute probability of B2. So of course it will depend on the color of the ball transferred from earn 1 to earn 2. Okay. So we will write R1 and B1, R1, B1 for events where red respectively black ball is transferred from 1 to 2. Okay. So we want to compute what is this probability. So that will of course depend on this. Probability of B2 is equal to probability of, well, B2 intersection with R1 plus probability of B2 intersection with B1. B1 being the complement of R1. But this is same thing as probability of B2 given R1 times probability of R1 plus probability of B2 given B1 probability of B1. And that is easily computed. What is it? So now you have transferred a red ball. Okay. So if you transfer a red ball, the composition becomes, so after R1, I'm going to write the composition for earn 2. So it will become now 5 and 5. Okay. Now after B1, let me squeeze that also here itself. B1, the composition becomes 4 and 6. Okay. And these are required to compute the required things. So here, given that R1 has taken place, it is 5 out of 10, 5 by 10 times probability of R1. I remember the composition 3 by 5 plus here this has become 4 and 6. So 6 by 10 times B1, that is 2 by 5. And you can simplify that. Okay. Simplify and get the answer. Fairly easy to simplify. Okay. Now, what is the other question? I suppose some other question was also there. Given that the black ball was drawn from earn 2, what is the probability that first ball drawn is red? Okay. So it's asking for probability of R1 given B2. Sorry, I have to go up and down like this. Probability of R1 given that the second ball drawn is black. So now you write this the other way around. Okay, probability of, I don't want to remember any formulae, and in fact it is advisable not to remember anything except the basic formula. And then just locally apply the formula. This is B2 given R1 times probability of R1 divided by probability of B2. And we just now computed B2. So we substitute the remaining things. They are all fairly easy to find out. By the way, this number in the numerator already appears in here. So we just copy that and simplify it. In fact, 3 by 10 divided by probability of B2, whatever it is. That is, so let us simplify that slightly. 3 by 10 plus, so 3 by 20, 3 by 25. I don't know if it helps to simplify. So multiply by maybe, I don't know, 50 throughout, 3 times 5. Here, 3 times 5 plus 3 times 2. So 15 divided by 15 plus 6, that is 15 plus 6 is 21. So 3 I could have cancelled anyway. So it's 5 divided by 7. Hope I have not made any mistakes. So I should warn you, sometimes I make mistake. But let me say one other thing, which will be a very useful information for you. Usually, if I detect some error after the lecture, before uploading, I correct it. Okay? So, yeah. Do I want to discuss other problems also? Let me see. What is the other? There is another problem I gave. Maybe I let you do this problem. This is actually worked out in the book. So there are very interesting exercises, examples given in the book. It's not possible for me, neither is it advisable to discuss solution to all the exercises or the examples. So you are encouraged to do as many problems as possible. The more problems you solve, the better will become your intuition. Let me do some other problems. Maybe these probably do not require. Bayes theorem, but doesn't matter. Here is a problem. Okay, let me, perhaps, I'm not sure if this is discussed in the book, but nevertheless, let us discuss this problem. So, probably this is also discussed in the book. Yeah, but there's some principle which I want to discuss. So let's do this. So let me explain. So, consider a series of hands dealt in a bridge game. Okay. So A be the event, I'll explain what that game is. That even that in a deal, in a given deal, each player has one ace, gets one ace. Show that the probability that A occurs in at least, show that the probability that A occurs at least once in 7 deals equals, or not equals, maybe, yeah, A occurs at least once in 7 deals. Yeah, this is what it, probability that A occurs is not equal but approximately 7. Approximately 1/2. Okay. So there are 52 cards in the pack, and in a bridge game there are 4 people, and the card is the you know dealt after you shuffle it thoroughly. The each person gets 13 cards. Okay, that's all we need to know about this. And A is the event that in a given deal, and of course, when it says series of deals, so what it means is that you deal the card once, and after the game, again, next game, you deal another time. Each person gets 13 cards, and so on and so forth. So the probability that A occurs at least once in 7 deals is approximately half. In other words, if you uh, yeah, so this is a bit of a surprise that in just 7 deals, uh, probability of each person getting one ace in at least one of the deals is half. Okay, that's indeed a surprise. This is also, there is also this birthday problem. So in any group of some 23 or 24 people, it's more likely that, I mean, it's a more than 50% chance that 2 people share the same birthday. So it's a small number. I mean, it's considering that there are 365 days, it's a small number, but nevertheless, this happens. So this type of counterintuitive things do happen. Okay, let us compute this. So first, let us compute what is probability of A. So probability of A is, so okay, before we can compute probability of A, you need to know, okay, number of ways. This you can just write like this, number of ways of dealing the cards. Dealing the cards. Or I will write it in a slightly more mathematical way of partitioning. Partitioning the cards into 4 piles, 4 parts of 13 cards each. So this is, let me not write this is total number of elementary events or cardinality of omega is equal to number of ways of partitioning chords into 4 parts. 4 parts, of course, labeled first, second, third, and fourth. Okay, and number of favorable events this is equal to, so you, okay, this is, so you divide this, let me write this is just 4 factorial. Sorry, let me write this carefully. So see, you have these 4 aces that can be distributed among 4 people in 4 factorial ways. Okay, times the remaining thing, it doesn't matter how you distribute it. There are 48 in all, but you must make it into piles of 12. Okay, for remaining cards are 48, and you want to make it into 4 piles, 12, 12, 12, 12. But within each one of these 12, the order doesn't matter. So actually, that amounts to 48 factorial divided by 12 factorial power 4. Okay, this is the main thing. So you understand. I'll tell you in a more general context how to do this. You imagine that you arrange these remaining 48 cards in arbitrary fashion. There will be 48 factorial ways. But within the first group of 12, it doesn't matter in which order you have arranged it. Okay, because the same person gets all those 12. And likewise, for the second person, in which order the remaining 12 cards were dealt, it doesn't really matter, and so on. Okay, so that is within each group, there's a 12 factorial possible arrangements, which you should all consider as one single group. So there is an overcount by 12 factorial times 12 factorial times 12 factorial and so on. So 4 times. That is 12 factorial power 4. This is the number of favorable events. So required probability is equal to how much? So yeah, and this I have not yet done. This is there is total number of cards is 52. The same logic as before. This is 52 factorial divided by 13 factorial power 4. So this is 4 factorial times 48 factorial divided by 12 factorial power 4. Whole thing divided by, this is the number of favorable events, total number of elementary events, that is 52 factorial. 52 factorial divided by 13 factorial over 4. Okay, so this you compute it. You can simplify it quite a bit. I will write it properly and leave it at that. 4 factorial times 48 factorial. I try to put the bracket instead of 48 factorial times 13 factorial power 4 divided by, actually it doesn't look, it is not such a horrible calculation. One can do it. but I will not do it. 52 factorial times 12 factorial power 4. Okay. And it turns out that this is approximately 1 by 10, which is what is required for the next subdivision. So show that the event A occurs at least once in 7 deals approximately. So the probability of A occurring once in 7 deals is approximately 1 by 2. Okay. So probability that A doesn't occur, probability of A complement is 9 by 10. And so this is for one, if you, for any one particular deal. So probability that when you deal the card 7 times and none of the times this occurs, so you can, so it's like tossing the coin 7 times, where probability of head is 1 by 9, 1 by 10, and tail is 9 by 10, something like that. So this is a complement, a complement, a complement, like this 7 times, a complement 7 times is equal to 9 by 10 whole power 7. And so this of course is 9 power 7 divided by 10 power 7. And presumably, I didn't check it, this must be approximately, okay. So the required probability is, we want A to occur, so this must be, I suppose, approximately 1 by 2. So somebody should verify this. I didn't calculate this, but this is something one has to verify. Therefore, maybe this is a little less. Therefore, the probability that A occurs,
Sir, it's 0.478.
0.478.
478.
Yeah. So this is a little less than this thing occurs. Thank you. Once, at least once, in 7 deals is approximately 1 by 2. Okay. Yeah, the more general principle, let me say that. So you have a set. So suppose that this type of combinatorial considerations enter into these calculations quite often. In fact, so the discrete probability, very much is very closely related to combinatorics. Okay, suppose that there are n objects which are partitioned into k subsets, okay? Say label them A1, A2, blah, 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 AK. And so they are Yeah, so the number of ways of so here I say subsets, not sequences. Sequences will be different. Within within each collection, within each AJ, ordering doesn't matter. Order of the objects do not matter. That's why I said sets. Okay. The number of ways of doing this, ways of obtaining. So before I talk about that, let me just suppose that cardinality of Aj. Sometimes I write like this: mod Aj is equal to lambda j. Okay, so that because it's a partition, I will have to have they are all disjoint, pairwise disjoint, and exhaust the whole thing. So this is equal to n. Then the number of distinct collections of sets or collection of partitions. Number of distinct partitions, that's what I want to say. Partitions is number of distinct such partitions is n factorial divided by lambda 1 factorial blah 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 lambda k factorial. And yeah, of course, you can recognize this as occurring in multinomial as a multinomial coefficient, and for this reason this is also written as n choose lambda. So this notation is also very much used, and we will continue to use them. I think I'll stop here, stop sharing. My plan is I want to discuss independence. I want to discuss this discrete probability for some more time. Then we will move on to more, random variables and so on. Maybe I'll stop today. Stop here for today. Okay.
Thank you.
If you have, we still have about 2 minutes. If you have any questions, you can ask. Yeah, somebody asked a question. I see a thing in the chat. Oh, okay. Good afternoon. Thank you. Any questions? There are many problems in the textbook. Please try as many as you can. Okay. I'll stop here.